Okay, welcome back, everyone. Today we are going to continue. We will finish with the decidable structures, and then we will start and hopefully finish as well what I want to tell you about computable structures. Okay, so let me remind you the definitions. So we had two of them: decidable structures and computable structures. And so for theories, it is pretty much the same thing. For structures, it is quite different. Yeah? Computable means that we can effectively check atomic facts, quantify free facts in the structure. And decidable means that we can check any first order facts in the structure, also with constants. So not just sentences, but formulas, yeah, with when we submit elements from the structure, that this is what we can check. Okay. So, and we are in this situation so far. So we talk about decidable theories and models of those decidable theories, in particular about decidable models of those decidable theories. So it is more kind of maybe logic approach, you may think about it, and this is more maybe algebraic approach if we think about particular structures. Yeah, when we talk about some kind of effective group, let's say, then we would naturally assume that the operation on the group is the effective thing, not that I don't know, word problem is effective or something like this. Yeah. So this will be more natural in this algebraic case. Okay, so I promised you that today we will start with a counterexample to the Watt's theorem, like the effective version of Watt's theorem about at least three models of a theory that it doesn't hold in the effective case. Later, I will show you actually a version which can be seen as an effectivization of Watt's theorem. You will see how it looks like. But for now, let's consider this counterexample. So it was the theorem done independently. So all those results from yesterday and from today, they're pretty old already, so mostly from the 70s and the 80s. And most of them were approved in the time when they were achieved simultaneously and parallel, independently in the West and in the East, in Russia. And so this is one of those results proved more or less independently and more or less at the same time by Millar and Kodai-Bergenov. And it states that there is a decidable theory, complete, with exactly two decidable models. Two non-isomorphic decidable models. And many non-decidable models. So it will not be a formal proof, but just some sketch of the proof, because I do not want to go into technical details that one needs to go through to do it properly. I just want you to have a feeling what happens there. So we start with a pair of non-computably separable, computably enumerable sets. So I assume that you all know what computably enumerable sets are. Okay, computably inseparable means there is no computable set that separates one from the other. Yeah? So we have those are CE, and we cannot find some computable set that contains all of these but none of these. Okay, those exist and are quite easy to build. So this will be our set A. Just let me check the notation. And this is the notation that I have. Okay, no, here I have the notation M0 and M1. Okay, let them be M0 and M1. M1, computably inseparable. C sets. Okay, and now we are going to code those sets into the theory that we are building. Okay, the language of this theory will actually be infinite, but computable. So we will have two kinds of predicate symbols, unary symbols pi, and binary symbols rj, binary. Okay. And those PIs will basically say that the universe is organized as follows. So we have P0, and then inside of this P0 we have P1, and inside of this we have P2, and so on, like this. Okay, and those relation R will be exactly the relations that code this complexity into the theory. Okay, so first thing that we need to say that if, okay, P0 holds on everything. Yeah, so for every x, P0 of x, and if some Pi plus 1 holds on whatever y, and for every y, if pi plus 1 holds on y, then also pi holds on y. Okay, so pi plus 1 is a subset of pi. And the second thing is, okay, saying that R, all R hold only on non-equal elements. Ri holds on x and y means that x is not equal to y. And the third one is the interesting one. This is the one that says how we code it. Okay. So if x is not equal to y, and okay, so let me write it just as a statement, not as a formula. If x is not equal to y, and ps of x and ps of y, and okay, and k belongs to M0 S, meaning we, so this is a computably enumerable set. We enumerate elements stage by stage, yeah, step by step. And this means that K belongs to the first, the S approximation of the set. Yeah? So in S steps, we get K here. In the set M0, then we say Rk is true on X and Y. Yeah? So this S is coded here, and this K is coded here. Okay, and 4 is similar. So this is the same, but here we have K enters M1 by the stage S. Then we claim the opposite, not RK on X and Y. Okay, then... Sorry? Yes. So these are actually many axioms if you formalize them. So it's a scheme. Yes. So that's what I said. It's not a formal formula. It's okay. That's the end. Yeah. Yes. Okay, and then we need to do some work that I will not do here. So there is still more work to do. It's kind of most smooth and homogeneous that I do not want to do here. But so, because the main idea is here, yeah? So the main idea that the universe is organized as written there, and the sets are coded in those indices, yeah? In those P indices and R indices. Okay, and here we do it more homogeneous, not in formal sense, but in intuitive sense. Yeah, to make it look more like well, yeah, to do it to have it more homogeneous. Okay, and if we do all of these. Yeah, so this is let's say this is our theory. The first 4 give us our theory T0, and this 5 stuff gives us some extension of this theory T0, which is not really important here. But what is important that this can be done in the way such that T is decidable and complete. And it has an effective quantified elimination. With quantified elimination. Okay, so this can be done just like this. So this is our theory. What can we say about our theory? So claim 1. If we consider 1 types, you all remember what types are, okay? So 1 types of this theory, all one types are either isolated, or, well, there is just one non-isolated, non-principal type, one type, one non-isolated type. And it contains exactly all of those PIs. So maybe let me just write it directly. How it looks like PI of X for all I. One type. Why is it so? So we have one type, we have just one variable. So how do the formulas look like theoretically? Yeah, they may contain PI of X, not PI of X, Rj of xx, not Rj of xx. Yeah, so these are, because of quantify elimination, those are just some combinations of those. Yeah. We have here that R must hold on different elements, x and y. So basically in one type, this cannot be there. So if there is anything, then always this thing. So it doesn't tell anything, okay? So we do not need those. So we only have some Boolean combinations of those two. And some conjunctions, disjunctions. However, we also have this property, yeah? So that each next one is contained in the previous one. So as soon as we get to something that looks like not pi of x, it will also mean not pi plus 1 of x, not pi of 2 of pi plus 2 of x, and so on. So the type that contains such kind of subformula will be p0 and p1 and whatever something, and not pi of x. So this will be the isolating formula for this type. So it will be an isolated type. And which means that it may also happen that we have all the PIs. Of course, this is a type of the theory, and this is, yeah, now it's clear, the unique non-isolated type. Okay, so claim 2. Claim 2, if we have at least 2 elements that realize this type, let's call it P. If in a model of T there exist at least 2 elements realizing P, then this model cannot be decidable in a model M. Then M is not decidable. Basically, because in this situation we can build a computable separator. How do we prove it? We assume that M is decidable. If M were decidable, then we consider a set let's see, the set, okay. The following sets, let me first fix some notation. Let omega of xy be the 2 type realized by those 2 elements in M. Realized by, at least 2 elements, let's call them C and D. Realized by C and D. Okay, then we look at the set S of all such n, natural numbers n, such that Rn of xy belongs to this omega. Am I correct? Yes. So This is a computable set because the model is decidable, thus the theorem is decidable, everything is decidable, so this type is computable. And so this set is computable. And if you look at the definitions, this is exactly what separates computably separates M0 and M1. And this just cannot happen. It's a contradiction. So that's it. Okay, it just follows directly from the definitions, from those definitions up there. Okay, so the next claim. If M has at most one element realizing type, this type P, then it is decidable. Well, why is it so? So we have a decidable theory, consistent, complete everything that you want. So it must have and a computable type. So it must be a model where this type, a decidable model where this type is omitted, and a decidable model where this type is realized. So those are the two. Yeah, so where it is omitted, it means that when we go like this, this goes to nothing. And where it is realized, it means that we have exactly one element there, one point that realizes it. And those are the two decidable models. Okay, so this is the result. Beautiful thing, I think. Yes. Well, there are quite some ways to code infinite language, also in finite languages, and maybe into graphs also. One should check if that would preserve decidability, but maybe you can find also some of those codings that will preserve decidability. So I do not think that it has to be. It's just natural for this example. I think you can do it also in finite language. Okay. Oh, actually, I do not exactly remember, but it's kind of to make it some kind of looking like Frese limits. So going in this direction. So saying that you have infinitely many things like this and infinitely many things like that, and everything that may happen should happen. So going in this direction. Okay. So let's continue. Okay, so let's start with computable structures. This is more modern direction. So most people work here, not there, though this will be to some extent also relevant for tomorrow's lecture. So I want, well, not this result in particular, but decidable theories, decidable structures. But you can see there that here the main topic was basically effectivizing model theoretic results and seeing if they hold or not in the effective case. So it was really like some kind of effective model theory. The main research here is not, or in many, most probably even cases, is not about models of some theories, but about structures. So this is our main object of investigation, structures. So it is mostly called computable structure theory currently, not computable model theory. Okay, so also to to stress that it is not only about models of theories. Okay, so the main definition, you remember, we have a computable set and computable predicates and functions on this set. And this is our computable structure. The a nice way, dynamic way to think about computable structures is being built stage by stage. Yeah? So if we think about a computable graph, how does it look like? So we have a graph G with some vertices and a binary relation. What does it mean that it is computable? Yeah? The relation here is computable, but if you think about it, if you think about this set as being enumerated stage by stage, so we have a first element, and then the second element, and then the third element, and so on and so forth. So as soon as elements appear, we also say how they are related to previous elements. Yeah? So if this is my first stage, I say, okay, those two are related, and they will still related forever. If this one appears, so let's say this is A, this is B, this is C, and at this stage we see that C is not related to either B or C or A, then this is how it will stay. So there will be no edge appearing at some later unpredictable stage. Okay, it might be the case that then some D appears and then C is connected to A through D. Yeah? So those two appear and this is how it stays then forever. Okay, so as soon as an element appears, we also define how this element is related or not related to the previous elements, and this is it. Okay, so this is a computable structure. There is also some research generalizing this to construct, for example, computably enumerable structures, which means that we have this set, and then some elements appear, and then C appears, but the edge may appear later. So it doesn't have to appear at the stage when A and B are here, maybe at some later stage or maybe not. But as soon as it appears, it stays there. Okay, so those are CE structures. I will not talk about them anymore today, just that you know that these things also exist, and these are especially useful when we talk about partial structures. For example, structure where we have some function which is not total. Okay, so this is an interesting direction for such situations. So our objects are like this, yeah, computable objects, and we stay here. And well, the main question here is what structures have computable presentation and what other structures do not have computable presentations. So what would be examples of computable structures? Well, okay, all finite structures, of course. All decidable structures, in particular dense linear order, Q. This is obviously computable structure, algebraically, like closed fields and things like this. So they are all also computable. So what else? A linear order, if we have just omega with a natural linear order, this is computable, not decidable anymore. So this is an example of a computable but not decidable structure. We will see later why. Okay, so I will show you why it is not decidable. Okay. What else? The standard model of piano arithmetic. Is as well here. Okay, and I will also show you that the non-standard models are not computable. This is what we will also do. Okay. Oh, okay. I forgot quite some stuff about decidable structures that I wanted to tell you. Maybe I will tell you later if we have time. Okay. Yeah, then things like random graph. Or some free group on infinitely many generators. And so on and so forth. So we have some examples here, but also quite some things that are known to be or to have no computable presentation. Okay, so what would be maybe the classical example of a structure that is not computable? So those are the so-called Daisy graphs. In many, well, most probably cases, when we construct structures here in computable structure theory, we usually code complexity using some sets into the structure. Yeah, like here. Yeah, we had two sets and we coded this complexity into the structure. So a Daisy graph, this is a very clear example how to code the complexity of a set into the structure. So suppose we have an arbitrary set X of natural numbers. Then we code it into a structure as follows. So this will be a graph with some special vertex C. And then from this vertex, we will have some cycles going like this. Okay, so many of them. That's why Daisy graph. Okay, and it basically says that if n is an x, so it's if and only if, the graph, Daisy graph G has a cycle, a unique cycle of size, let's say 2n plus 2, just to be sure that this is really a cycle, even if 0 is there. Okay, and n is not in X if and only if G has a cycle of size 2n plus 3. Okay, and these are the only cycles that live here, and exactly either one cycle of this size or one cycle of that size. Okay, and then the atomic diagram of this graph G has a complexity exactly the same as the set X. Yeah. So first of all, if we know the set X, then of course we can find out about everything about G. And second of all, if we know G and we want to know whether or not some n belongs to X, then we just wait for a cycle related to this n to appear. So one of those will appear for sure at some stage, and this is when we will know the answer about X. Okay, so the atomic diagram of G has exactly the complexity of this set X. In particular, when X is not computable, this daisy graph is not computable. So this is a non-computable thing. Okay. So, in general, it is quite hard to describe when a structure, like to find some conditions on a structure from a particular class that guarantee that this structure will be computable. So in most cases, it is pretty much impossible to do. So we cannot say that the linear order is computable if and only if something similar and nice happens. So pretty much the only, one of the very few examples that I know is about equivalent structures. So what is an equivalent structure? E is an equivalent structure. So again, we have some set as the domain. Let's not call it E. Let's call it whatever. S, A, let's call it A. The domain and the relation E. So this is an infinite set, and this is just an equivalence relation on this set. Okay, so very simple structures. What would be an example of a obviously computable structure? For example, an equivalent structure with infinitely many equivalence classes of size 1 and infinitely many equivalence classes of size 2. And so why would it be computable? What would be a very, very effective presentation of this structure? So we say 0 is in its own equivalence class, is not equivalent to anything else but to itself. Then 1 and 2 are related to each other. 3 is not related to anything but itself. 4 and 5 are related to each other, and so on. So to check E of xy is very easy. So we only have either x is equal to y equals to sine 3 times k for whatever k, or x is 3k plus 1 and y is 3k plus 2, or vice versa. So this is the definition that shows clearly that this is a computable structure. Okay. There are actually more of them here. I will write you the properties that guarantee that the structure has a computable presentation. They look somewhat confusing, but this is just as you do not have to really understand what's going on here. It's just to give you a flavor that this is a difficult question, that even for such simple, very simple structures, even though we have a description how all of this looks like, but one has to work to get it. And for more complicated classes, there is little hope to do it. So these are more kind of examples, or like natural, hopefully, examples from some classes with some effectiveness properties and so on. Okay, so an equivalent structure has a computable presentation. Has a computable presentation if and only if the following two conditions holds. First of all, a special set related to this structure called the character of the structure, which is the set of pairs n and k such that A has at least k classes of size n. is sigma 0, 2. So it's not too complicated. So this means the set of equivalence classes of size n. And so the number of classes of size n is at most k, where k is a natural number. And the second one of the following three conditions must also hold. So, by the way, these are results by Harizanov, Sensor, and other people. I forgot to write down how, but for sure Harizanov and Sensor and someone maybe colored. I have to look up exactly. Okay, so one of the following holds: either the set of the set of numbers of classes. The set of sizes of classes that have some elements there is finite, or number two, we have only finitely many infinite, we have infinitely many infinite classes. Or there exists a computable function such that, like for computable function f of ns, such that for every n, it is non-decreasing in S, and has a limit it's called f star of n, which is a natural number greater than or equal to S. And this exactly describes, well, and not exactly describes, and the structure has equivalence classes of this size. Okay, so as I said, this is confusing and not very intuitive, and probably not really helpful at the moment. But yeah, take it as just as a fact that we have some description. It is useful, but even in this situation, it is not like the very simple thing. The idea of all those properties, especially this property and this property, so this is pretty much obvious that if this happens, then the structure should be computable. But we use those two just, so suppose we have an arbitrary, not necessarily computable copy of our structure, then we use, and we have this set being sigma 0, 2, and one of those hold, then we try to use this information to build our classes according to the sizes that are given here, but it is just a sigma 0, 2 set, so it may say in quite some situation, I was joking, this is not what's happening in reality. Yeah. And then we need to have some trash to put everything that we have built using our stage-by-stage construction. To say, no, this is not how the structure looks like, and we need to put all of this, we cannot just erase and say, okay, those are not equivalent anymore. So we need to put them somewhere, and we put them either here or here, for those who know these things. Okay, so this is one of few classes that do have complete description how computable structures from this class look like. Another class that has a description, those are models of Peano arithmetic. So this is theorem Tannenbaum, that only the standard model of Peano arithmetic is computable. Okay, so it holds actually also about weaker theories, about Robinson's Q. I think this also holds like everything where one can represent computable functions. This will be true. Okay, computable facts. Representing computable function, when I say that a computable function or computable whatever fact is representable, I mean there exists a formula such that this formula follows from here if and only if the function whatever like f of n equals k if and only if we can prove some formula associated to this function in Peano arithmetic. Okay, so this is the representation. Okay, so let's prove this. We will use again the same computably inseparable sets. Okay. Proof. Okay, so let's prove it and then have a coffee break. What was our notation? M0, M1. Let M0 and 1 be computably enumerable, computably inseparable sets. Computably inseparable sets. So, okay, so our facts that we will code as formulas here are the following. We will say X belongs to M0S, yeah, Y belongs to X belongs to M1S. So this is a computable fact. It can be expressed using using the language of Peano arithmetic. Okay, and this is also, so we can say there exists a stage such that by the stage S, sorry, we do not need to say that there exists a stage. So by this stage, we enumerate X into here. So basically saying that the corresponding function, whatever phi E0 by the stage S on X converges. Phi E1 by the stage S on X converges, where those indices correspond to these computably enumerable sets. Okay, so we can express it in Peano arithmetic, in the language of Peano arithmetic. We can also say that whatever element is divisible by whatever prime number. So we can say things like some prime number py divides an element u. Yeah? So this is also a computable fact. So we have a formula for this as well. So we use this to build a new formula, psi of x and u. And this formula will say the following. It will say for every y, let me see how many I need, 3. If there exists and S less than or equal to X such that Y belongs to M0S, then Py should divide U. Otherwise, if there exists an S less than X such that Y belongs to M1 by the stage S, then Py does not divide U. Okay, so the big one. Okay, so this is our formula. And now, well, if we have some, you remember we are in a non-standard model of arithmetic, yeah? So we have a standard part and non-standard part, some infinite elements somewhere there. Yeah? So if we consider this formula C on some finite element C and U, yeah? C is finite, then of course we can find a U such that all of this holds. Yeah? So if there exists an S less than some C, so if we, by some finite stage, we find out whether or not Y belongs to this set or Y belongs to this set. If we know one of those, then, okay, we choose the corresponding Py, and we say it is in our U, so U will be basically just the product of those Py1 times Py2 times Pyk, where those Ys correspond to this situation, and there will be no Pys that correspond to this situation. Yeah. So U will be divisible by anything that corresponds to Ys from the first set, and will not be divisible by anything that corresponds to Y in this set. Yeah? So if we have this finite bound, then of course in finitely many steps we can do this. Okay, so in our structure we for sure have that there exists U, C of Cu is true for every finite, for any finite C. And this means by overspill that there exists also an infinite element there where this is true. Let's say C prime, such that the same thing holds. And, well, that's pretty much it. So let's consider what is the witness. Let's say the witness is D. Let D be such that in A we have C is true on C prime and D. Then we just take the set consisting of all the natural numbers such that in A we have that Pm divides D. This is a computable set, yeah, because we assume that A is computable, and this is a computable fact that we check in A. And so this is a computable set, and it contains all, so it separates M0 from M1. So it will contain everything that corresponds to this situation and nothing that corresponds to this situation. Okay. And this is again a contradiction. So this cannot happen. We shouldn't have a computable separator. So a non-standard model cannot be computable, and much less decidable or anything. Yeah. So the standard model of Peano arithmetic is also computable but not decidable. Okay, so let's have a break here, and we'll continue with other results then.